Okay, on example one, we're asked to evaluate trigonometric functions. Before we do that, I want to make a hopefully brief aside where I can kind of talk about this idea of a trigonometric function again. So when we think of a function, we think of something that has inputs and outputs. So it's kind of like a little machine and it follows some rule. So for example, for this function, f of x, we put in a value for x. So we put in 3. Well, our rule is that we take our number, we multiply it by 3, and then we add 5. So for this function, when we have an input of 3, we have an output of 14 altogether. And that's kind of our function. So we think of this function as doing something to our input, right? We have an input, and this function does the following thing. It multiplies it by 3, and then it adds 5. So when you hear trigonometric function, when you hear like sine of 30 degrees, and we get out 0.7. Okay, so that was kind of the example I was using a few times, was like a 30-degree angle, something roughly about like that. The sine is the sine opposite over hypotenuse. I don't think I quite drew that like a 30. That's probably too big. Okay, so sine is opposite over hypotenuse. Looking at these, we can say that this looks about 70% as big as the hypotenuse, roughly, maybe not a perfect drawing, but if you put it into a calculator, that's what you would get. So you have sine of your angle equals some ratio. That is what the function is doing. The input is the angle, and the output is the ratio. Now the question is, what is this function doing though? Like, what is it doing to take the number 30 and produce the number 0.7? What is the series of steps, right? Like in that other function, we tripled it and then we added 5. What is the series of steps that this thing is actually doing to produce this number? Okay, so there's two ways to approach this. One is to understand that originally, I believe I'm accurate in saying this, originally there was not a series of steps. So originally there were just tables. And what the function was doing was effectively just like it was a person looking into a table. So if you said, well, what is it doing when we say the cosine? Well, we'll do cosine now. So the cosine of 30 is, I think that says 0.86. So like, the input is 30 degrees, the output is this ratio of 0.86. What was done to produce that information? Well, what was done is somebody physically measured a triangle with a 30-degree angle and just figured out what that ratio always is and recorded it. So at a certain point, that's what we would have done. I think there's points at which we would have had calculators that probably just had tables of values programmed into them that they would reference to find the answer. Now, that's not really what I think they do anymore. What I think they do now is something slightly different. I just want to talk about it for a moment because this is something that when I was learning this subject, it always kind of puzzled me. Is like, what are these functions? Like, what are they doing? And the reason why you don't get an answer typically is because the answer is fairly complex. So I'll kind of jump to the point. There are ways that you can use calculus to describe what this function is. So first of all, kind of, we'll jump ahead to say, what does this function look like over time? Well, we get this function where as the angle increases, that ratio increases, then it decreases, then it increases, and it's cyclical. It just goes on forever. Where x-axis is our angle in this point. So that's our input, and our output, that ratio, is the height of this line as we go across. Now, there's a way to generate this line as like an actual equation that we would understand as having like an input that we could work with in the same way as our linear equations. And it kind of looks like this one right here. So let's just try this out. So we have x, and then we say minus x cubed over 3 factorial. And then we do plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. As we do this, what we do is we kind of take this green line and we start making it hug this sine function closer and closer. And the further out I follow this pattern, so if I added x to the, I think the next one would be x to the ninth over 9 factorial, the longer I do this, the more and more closely this green line starts to hug this sine function. So if you wanted to think of like, what are we actually doing when we put in the number 30 degrees and we get out 0.7? Well, we're putting it into this long series, right? We've talked about series before. It's like a series of steps that get added or subtracted. Now, where this idea came from, like why does this match that sine function over time? That's something that if you're interested in that YouTube channel I've talked about, 3 blue 1 brown has a very good one that talks about where this comes from. And the title of it, if you're interested, is Taylor series. So Taylor series, and that's what this is. It's a Taylor series. So what's actually being done by your calculator when you type in, sine of 30 degrees and it tells you what that output is? It's a fairly complicated series of steps that require some advanced calculus ideas to understand, where does this all come from and why is it that over time, if we continue this pattern out forever, these alternating negatives and positives of these odd number exponents over odd number factorials, this big complicated looking thing that keeps going, right? Dot 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 keeps going. Why is it that actually produces? Why is that equivalent to this sine function? That's something for you to investigate on your own if you're interested. But I do want to just point out that there is an answer to that question of like, what is the sine function actually doing? And this is kind of a description of what that answer is in one way of looking at it. Now, the other way of describing it, which I think is probably better for us at the moment, is just to think about those tables, just to think about the fact that these ratios are standard values. So if I have like a 45-degree angle, the sine of that 45-degree angle, the opposite over the hypotenuse, will never change, no matter how big that triangle is. That ratio of the opposite side to the hypotenuse is the same for every triangle that includes a 45-degree angle. Okay, and we can just kind of reference those known values to manipulate these images to understand what the answers should be to different questions that we're getting, and to kind of understand how to fill out all the information on a triangle given some starting information. So the end goal here is to be able to take one side length and one angle and use these tables of values in order to fill out all of the remaining information, the other 3 sides and the other 2 angles. Okay, that's kind of the end goal of this early trigonometry. So here, let's kind of fill out what they want for example 1. So they're saying the sine is opposite over a hypotenuse, so tangent is opposite over adjacent, TOA, and sine, cosine, and tangent. Cosine is ka, adjacent over hypotenuse. So they want us to fill those in. Well, they're saying from this angle, so the opposite would be 28, the adjacent would be 45, and the hypotenuse is 53. So adjacent over hypotenuse would be 45 over 53. The cosecant, which was the flipped over version of sine, would just be these numbers flipped over. It'd be 53 over 28. And cotangent would be your tangent flipped over. So it'd be 45 over 28, right? The adjacent side over the opposite. And that's all it would take to kind of fill out these answers when you're given these values and you don't know what the angle is, right? So this is a scenario where we don't know exactly what that angle is, but we are going to describe some trigonometric functions being applied to that being applied to that angle by knowing what the ratio is that gets produced. Okay, so we're saying that we have these functions, we apply the function to this angle, and the output should be a ratio. And we can know what the ratio is if we already know what the side lengths are. Okay, so I think that is it for example number 1. Let me just double check. Yes, we'll move on to the next example in the next video.